So this is, I guess we could say this is chapter 4. It's called Dynamics, Force, and Newton's Laws. Really, it's just about forces and causes of motion. In chapters 1 through 3, and really just chapters 2 and 3, we studied kinematics, which is motion, or the study of motion. That's what kinematics is. A lot of this was worked out by Galileo and others. It was really in pretty good shape by the time Newton came along in 1642. He was born in 1642 to 1727, and they had the Julian versus Gregorian calendar in there, but he and Galileo essentially, he was born the year Galileo died, depending on which calendar you look at, and then he died in 1727. So he lived a long time. Newton was interested in causes of motion. So kinematics was just, when we were working on all those problems, we didn't actually say, you know, how did the car start to move, or what caused the ball to accelerate as it fell, or any of that stuff. We just accepted that it was moving, and then we solved problems based on how it was moving. That's what kinematics is. But Newton was interested in what causes things to move, and this field is called dynamics. And it deals with forces. Forces are the things that cause objects to move. So Newton came up with 3 laws of motion, really 4, if you include gravity, that describe how things are caused to move. And that's really what this chapter is about. And so we'll be talking mostly in this chapter about forces and how they work and how they cause motion. So forces are vectors, and so just like all the other vectors we've looked at, they obey vector math. And so, you know, if we have a boulder here, and somebody is exerting a force on the boulder, right? And we'll call this force F1, right? And then over here, somebody over here is pushing on this boulder, right, this way, and we'll call this F2, right? And so we're looking at what's happening to this force, and you might imagine that the net force on this boulder would be, you know, off in this direction, F net, right? If one of them's pushing this way and one of them's pushing this way. Notice we're not really talking about how the boulder is pushing on these people who are pushing on the boulder, or other forces. We're just looking at what's happening to the boulder. Often we want to isolate an object. And so we just say we're just interested in this boulder in this problem. And so we do this with what's called a free body diagram. We'll go over this in some detail through the chapter. But so if we were just interested in the boulder, in a free body diagram, that's our boulder, right? We just isolate an object. I'm not interested in the people. I'm just interested in the boulder and what's happening to it. And so I would do this. I would say, look, I've got a force going this way, that's F1. Maybe I want to call these guys vectors specifically, just to be careful, right? Oh, sorry, that's F2. Got it wrong already. And there's F1, right? And so now I've isolated my boulder, and this is my free body diagram. And I've identified the forces on it, and I don't have to worry about the rest of the clutter in the problem, the people or whatever is causing these forces, right? And then if I want to start doing some math on this, I kind of have to identify a coordinate system. So often I will do that. I'll put a little coordinate system in there. And now, I might say, well, what's happening to this object? Well, it's experiencing a force due to two vectors. Well, so the net force is going to be the sum of the vectors, and so I can take this vector and put it over here, like that. There's my F2, and I can say, look, the sum, F net, I can say that the sum of those forces is just the net force, the vector sum, right? And so in this problem, I would say, if I wanted to just erase this down here, I would say F net is equal to the square root of F1 squared plus F2 squared, assuming they're at right angles, right? I was kind of drawing them that way. And then I would say, theta, if I want to call this angle theta, I would say theta is equal to tan inverse of F2 over F1. And so I have these forces acting on this thing, and this drawing this free body diagram and doing a little math allows me to tell what the magnitude of the effective force is, right? And what its direction is relative to the coordinate system that I identified. So we do a lot of problems like this. We'll often have multiple forces acting on an object, and we'll be isolating an object. Usually it's a car or a ball or something like that, and we'll look at all the forces that are acting on it, and then we'll do some kind of calculation, and that calculation will tell us what's happening to the ball, what's causing it to move, if it's moving. So here's an example that you can work on. This is a sled. Two dogs are tied to a sled. Fido, okay, that's my picture of a dog, with apologies. Fido is pulling straight forward with a 50-pound force, right? Lassie is pulling with 100 pounds force, 45 degrees. This is the sled. Maybe that doesn't look like a sled, right? And so two dogs are tied to a sled. Fido's got a 50-pound force that way. Lassie's got a 100-pound force, 45 degrees that way. And so you should be able to get F net. It's about 140 pounds. And the angle is about 30 degrees relative to the vertical. And you should start out with a free body diagram that's got a force going this way. FF equals 50 pounds, and FL equals 100 pounds. And maybe your coordinate system looks like that. So you should be able to work that out and solve that and get those solutions, right? So we've talked a little bit about forces, and now we're going to talk a little bit about Newton's laws of motion. Newton was interested in causes of motion. Galileo spent much of his time in physics working on kinematics. That's the work we did in the chapters 2 and 3 on how things move, position, velocity, and acceleration. Newton wanted to understand causes of motion, and so he talked a lot about forces. So he set out 3 laws of motion, which you probably know already. Here's the first one. It's an object at rest or in motion remains that way until acted on by a force. That's the sort of the layperson's version of that. Sometimes it's called Galileo's law of inertia. More specifically, you could say, or using more precise language, I guess is the way to say what I want to say, an object with a constant velocity remains that way until acted on by a net external force. See, we've already defined what velocity is, right? Velocity includes both speed and direction, how fast it's going and which direction it's going. And so an object's doing that. By the way, a zero velocity is also constant if it's staying at rest. So this kind of includes the at rest part. An object with a constant velocity remains that way until acted on by a net external force. And so this is a little more specific language, right? It's a force is, we've kind of talked a little bit about forces, right? If you should have some sense of what a force is. It's a push or a pull, or a tug or a yank or a lean on or something like that, right? An external force is a force that comes from outside the object, right? If I have a calculator here, there's all kinds of internal forces in the calculator and this marker, the atoms pulling on each other, holding these things together, right? So they don't just come apart when you pull them apart. Those forces don't count. You can't sit in your car and push on the steering wheel and make your car go forward. And so the force has to be external. The net means it can't add up to zero. If you have two people pushing in the opposite direction on a car with equal forces, then the car won't move because the net force is zero. There are a lot of times where the net force is zero. Here's a little a Swasu bulldog, right? There are some forces acting on it. Gravity's pushing down on the dog, the table's pushing up on the dog, but the net force actually adds up to zero, and I'll tell you why I know after we talk about Newton's second law. But there are often cases where forces are acting on something and they add up to zero, and so there's no net force. There can be multiple forces, but no net force. And so that's Newton's law of motion. No, that's Newton's first law of motion. See if you can think up what the second and the third law is. You've probably seen them around, and you've for sure heard the third law. The second law is an equation, and it has three letters in it. So it's F equals mass times acceleration. And this is technically the net force. And really, if I want to be real careful, I would say the net external force is equal to the mass times the acceleration. This is a vector, and this is a vector. And so this is the mass, and this guy is the acceleration. And so this is what Galileo was kind of after. Newton was kind of after. He was after the relationship between forces and motion. And this kind of gets it. If I rearrange this equation, I get the acceleration is equal to the force divided by the mass. Mass is not a vector, right? And so I'm just putting the vectors. We could just drop the vector signs and talk about 1D, one-dimensional motion, straight line motion. The acceleration you get is the net force that's applied divided by the mass. And so for a given force, the bigger the mass, the smaller the acceleration. So if I push on a shopping cart that's empty with a certain force, 30 pounds, right? The acceleration I get will be that 30 pounds divided by the mass of the cart. But if you fill the cart up with groceries and I apply the same force, there'll be a much bigger mass here, and so I'll have a smaller acceleration. That's the idea. And so So we're going to assume this is the net external force, right? So this is just somebody pushing on the bag of potatoes. And so we can say, look, the acceleration is the force divided by the mass. That's 40 newtons divided by 10 kilograms, which is 4 newtons per kilogram. And we say, well, how is that a unit of acceleration? Well, we have to come back up here and look at what the units are, right? And so let me come up to the top and say, the units for force. Well, if I say force is equal to mass times acceleration, and so the units for mass is kilogram, that's the SI unit, and the units for acceleration, we've already done this, that's meters per second squared. And so the units for force is kilogram meters per second squared, and we define that to be a Newton. And so the SI unit for force is a Newton. And so that's 4 kilogram meters per second squared over kilograms, because a Newton is a kilogram meter per second squared. The kilograms cancel, and I get the acceleration is 4 meters per second squared. And that makes me happy because the unit comes out to an acceleration. Meters per second squared is an acceleration. So I'm going to talk a little bit about the normal force, just to introduce another force here. And I'm going to say, look, the normal force occurs between objects in contact. There's something called the contact force, and the normal force is the part of that that's perpendicular to the contact surface. The part that's parallel to the contact surface is called the friction force. And I'll come back to the normal force, and we'll talk about it more as we go. But I'm just going to give you a little example here. Here's a cup sitting on a table, right? And so since the cup is at rest, we know its acceleration is 0 because it's at rest. If it's not moving, its acceleration has to be 0, right? And what that means is, by Newton's second law, F net external equals the mass times the acceleration, right? What that says, that's Newton's second law. The net external force equals the mass times the acceleration, but that just has to be equal to 0, right? F net external equals 0 because the acceleration is 0. So the right-hand side is 0, and so that means the net external force is 0. And the net external force, F net external, is just the sum of all forces. That's what the net force means. It's the sum of all the external forces. The net is, you add them all up like vectors and you see what you get, right? And so this term means, the sum of all, or something like that. That's a mathematical term, right? That's the Greek letter sigma. I don't know if I can draw it any fancier than that. It looks like that. Sometimes they put little hitches there or something. Anyway, so you'll see me write that occasionally. But let's look at this cup, for instance. And right away we know that gravity is pulling down on it because it pulls down on everything, right? Gravity is pulling down, so there's a force going this way. And the force of gravity, as we just showed, is mass times gravity. Sometimes, we refer to that as the weight. These are just, force of gravity and weight are two different ways of saying the exact same thing. They're not two different things. They're exactly the same thing. They represent the same thing. They're just two different words that mean the same thing. It's like dog and canine. And so I know there's one force acting on here. If the net force is 0, right? If the net force is 0, there has to be another force. And the other force is the table pushing on the cup. And if you take your cup, if you grab a cup, here's my cup of water, and you push down on it, you can kind of see, maybe not. If you push down on it, that it gives a little bit. The table, the whiteboard underneath it gives a little bit the harder I push. And so I can kind of feel the table pushing back up, or the whiteboard pushing back up on my cup. And this is the thing we call the normal force. Technically, like I said, it's actually the component of the contact force. The contact force is a force between two objects that are touching, right? It's the component of that that's perpendicular to the surface. The component of the contact force that's parallel to the surface is called friction, and you know that one already. We'll talk about that some as we go. So the normal force is a force that's perpendicular to a contact surface, and if you keep your eye out for them, you'll see them a lot. Normal forces come along all the time. And so this is the normal force on my cup, and this is why my cup doesn't go anywhere, because even though gravity is pulling down on the cup, the table is pushing back up on the cup. And so the net force, the net external force on the cup is 0. So let's just do an example. So I have 4 thrusters, each exert force T on the back of a rocket car. So here's my rocket car. And I have 4 thrusters on the back. Right, and I should probably give them some and so each of these thrusters is pushing with a force T. On the car, there's a force going this way, F, which is the force of friction, which is equal to 650 newtons. Maybe that's the air resistance or the friction from the road or something. My acceleration is 49 meters per second squared, and the mass of the car is 2,100 kilograms. And so if I draw a free body diagram for this, I can have 4T going this way and FF going that way, and I have an acceleration going this way, which is 49 meters per second squared, and I can draw a little coordinate system like this, y and x, and I can say, look, the sum of the forces, well, let me write it all out so we get it right. I can say, look, the net external force, which is the sum of the forces, which is 4T minus FF, right? These guys are going in my positive x direction. This guy's going in my negative x direction, equals the mass times the acceleration. Right? I'm after T, and so I can just look at this piece of the equation, and I can say 4T equals force of friction plus ma, or T equals force of friction plus ma divided by 4. That's my thrust. Right, and so maybe I'll have to erase some of the top of the problem. If you want to reread it, you can roll back the screen, right? And so now my thrust is equal to my force of friction, which is 650 newtons, plus 2,100 kilograms times 49 meters per second squared, divided by 4. And what I get is about 2.6 times 10 to the 4th newtons. That's my thrust.